This series of videos is going to look at applications of vectors with force and equilibrium. Now, to start with, if you haven't heard of what a force is before, and you probably have in science, a force is a measure of the strength of a push or a pull. Now, forces can start motion, stop motion, make objects move faster or slower, and change the direction of motion. Now, focus will be on forces that cancel each other out. So what we mean by that is we're looking at equilibrium. Now, force is a vector quantity. It has both magnitude and direction. Now, we're going to assume a force is acting on a single particle, a point at which the entire mass of the object is concentrated. And that's what physics is based on. So let's start by looking at weight. Every object on Earth is subject to the force of gravity, or the weight of the object. Now, weight acts vertically downwards towards the center of the Earth. So we have this vector, which is weight. Now, the standard unit of force is the Newton, and its units are also expressed as kilograms per meters per second squared. Now, let's look at an example. A person with mass 80 kilograms weighs. Force is mass times acceleration, so that's going to be the mass of 80 times by gravity. So note this G here is gravity. Now, we normally take gravity as 9.8 meters per second squared. That's on your formula sheet. So I've got 80 times 9.8, which is 784 kilograms per meters per second squared. And because 1 kilogram per meters per second squared is 1 newton, we can express that as 784 newtons. So note 1 kilogram per meters squared is equal to 1 newton. Now, resultant force and equilibrium, when a number of forces act simultaneously on an object, their combined effect is called the resultant force. Now, the resultant force is the vector sum of the forces acting on the particle. We've been dealing with that kind of thing already. But if the resultant force acting on an object is 0, the object will remain at rest or continue moving with constant velocity. So it means it has no effect, and the object is said to be in equilibrium. Now, a normal force, any mass placed on a surface experiences a normal force perpendicular to the surface. Now, that's what's called a normal force. Whenever you see the word normal, you need to think perpendicular. Okay, now the normal force keeps the object in equilibrium. So you can see two diagrams here, one where the weight is going straight down, so the normal force goes straight up. You can see that it's perpendicular to the surface. In the next diagram though, we've got this inclined plane, so what we need to do is we need to follow down our normal force, and there is our right angle. Okay, so that normal force is at right angles to the ground, or to that inclined plane. Our weight is going straight down though. So you can see how those two diagrams vary. Now, tension force, the diagram, as you can see here, shows a string attached to the ceiling supporting a mass. Okay, so this is the ceiling here, and this is my mass. So this here is the string supporting the mass. Now, what you'll notice in this case, we still have our force of gravity acting straight down. Okay, so that's our weight. We also have tension in the string. Okay, so we have tension upwards on the mass, And we also have a force equal in magnitude but opposite in direction acting on the ceiling at the point of contact. The force exerted by the string is called the tension force. Now let's put this into practice and we'll do some examples and hopefully it'll make more sense.